Okay, great. I think we're ready to get started. Okay, well, welcome. We are thrilled to roll out the latest episode of the Quantum Seminar series dedicated to the research and academic quantum communities. This seminar takes place every Friday afternoon at 12 Eastern Time right now and is hosted on the Qiskit YouTube channel. I'm your host for today. My name is Olivia Lanes from IBM Quantum, and I'm very excited to be here today speaking with Professor Jason Cong. Let me introduce Jason really quickly before we get started. So Professor Jason Cong is the Volganu Chair for Engineering Excellence and the former department chair at the UCLA Computer Science Department with a joint appointment from the Electrical Engineering Department. He is also the director for the Center of Domain-Specific Computing and the director of the VLSI Architecture, Synthesis, and Technology, the VAST Laboratory. Dr. Cong's research interests include novel architectures and compilation for customizable computing, synthesis of VLSI circuits and systems, and highly scalable algorithms. He has close to 500 publications in the area, including 15 Best Paper Awards, 3 10 Most Influential Paper Awards, and the first paper inducted into the FPGA and Reconfigurable Computing Hall of Fame. He and his former students also co-founded Auto ELS, which developed the most widely used high-level synthesis tool for FPGAs. He was elected to IEEE Fellow in 2000, the ACM Fellow in 2008, and the National Academy of Engineering in 2017. All right, so welcome, Professor Cong. Thank you so much for being here today. How's it going?
Doing fine. Thanks so much, Olivia, for the introduction.
Sure, no problem.
Yeah, can everyone hear me all right?
I can hear you.
Okay.
I think we're ready to get started, so we'll just pull up your slides. And as a reminder to everybody, we can take questions throughout the seminar today, and I'll do my best to interrupt Professor Cong very politely when they arise. And we'll also leave some time at the end, if we can, for more questions. So whenever you're ready to get started, I'm really excited to hear about this one.
Okay, great. I'm also excited. This is actually my first YouTube live streaming talk. Let's see how that goes. The topic today, I know it's quantum computing series, but it has more of a computer science flavor. We're going to talk about the layout synthesis is what the major steps in quantum compilation. We're going to talk about the gap analysis and the optimal solutions. A little bit about my background. Olivia already mentioned I've been a faculty member at UCLA for 30 years. Most of my research is actually on VLSI design, the automation. Which is the VLSI is the working horse right today for information processing. If you're keeping track of Moore's law, that we already have chips over 19 billion transistors. I think just in a matter of weeks will go across 100 billion. And I worked on all the design phases from high-level synthesis. You take a C program, you get a VHDL, Verilog, and you get the logic descriptions. That's for the logic synthesis. And then you do a technology mapping. For example, you have certain gate sets at the end foundry can implement, and then finally do the physical design, the place and route these ones. So my view today will be somewhat influenced by my past experience in the VLSI world. If you switch gear to look at what happened in the quantum world, it's a very different scale. That, for example, I start getting interested in this area around 2015, 2016. At that time, if you read the paper around, there's this 4-qubit device out of a UCSB. But nevertheless, that my friends in quantum, both industry and academia, they promised that the scaling will be as fast as VLSI devices, which seems to be true, right? If you look at this curve, it shows you the devices from Google, from IBM. This is on the exponential log scale. So you can see number of qubits doubles from 4 to 8 to 16 to 32 to 64. So there's looks like it's early days of the Moore's law. And if you look at the Rigetti, that's a similar trend. And there's also different type of technologies, IQ, and it's another one out there. So the question is that how do we write program to compile to these devices? Before we go there, because we have a very diverse audience, let me give a very quick introduction. And for us in sort of in computer science, we're familiar with the binary representation zeros, ones. But the quantum is actually give you a richer set of representations that can be superposition of any of the zeros, ones. And then you can have multiple qubits, and then they can be actually composed together to get a higher dimension in the Hilbert space, and you can also have superpositions of that. And the message I want to show is that you can manipulate these quantum bits either by simple single qubit bits like flip gates, Hadamard gates, and the phase shift gates. For example, IBM has this very powerful, very universal three input single qubit gates with three input parameters. And you can also have two qubit gates. The most widely used one is a CNOT control gate that where you can, if the first bit is a 0, you don't do anything. If the first bit is 1, you will flip at the second bit. The amazing result is that it shows that with these very simple bits, for example, the bit flip, and then on Hadamard gates and some phase shift, and together with the CNOT, that we can do universal computation. So in that sense, that it's give us a complete set of building blocks to do computation. Now the question is that how do we do that? And this is the rough flow I kind of summarize. We start with applications. For example, the suitable applications the community is looking at is the chemistry, simulation, optimization, machine learning, cryptography, and you come up with the best algorithms. So typically you represent it in some kind of a linear algebra representation, and then you do logic synthesis. You map it to the set of generic gates I talked about. And then you do layouts. You have to go to a particular device that from IBM, from Google, from other companies. So that's what I call layout synthesis. You do the space-time coordinate computation for all the gates. And then you generate control signals and this waveforms of the control signals as the input to the devices. The last step, it involves a lot of physics, right? That depends on what kind of devices you have, superconductor, trapped ion, silicon, optics. So this is the research focus of my lab, goes from logic synthesis to the signal generation. So this is very similar to the kind of a design automation or compilation step of a traditional VLSI design. So one problem we focus on, if I go back, is that we want to take a bottom-up approach, that we are looking at the layout synthesis, the first step. So what's exactly the layout synthesis problem? We can these days write a quantum program. It's very primitive. It's like an assembly program, but basically it's at least a sequence of gates you're going to apply to the input. And if you draw it as a circuit diagram, you can say on qubit Q0 apply the gate G0, which is a bit flip, and so on and so forth. And so that's just the logical circuit diagram. The actual device, for example, from IBM, the QX2 has 5 qubits. So now the question is, how do I map this circuit to this 5 qubit device? You can say, okay, I have a few 4 qubits. I will put them this way, and then I can actually schedule the gate one by one. G1 goes here, and I will do the G1 operation. This gate G3 goes here, Q2, Q3. That's fine. Because remember, this is a CNOT gate. It involves a pair of qubits. Now, after a few steps, you want to do this computation, which is a G10 that involves G0 and the G3. This creates a problem because these 2 qubits are not adjacent on the device. So what I've shown here is the more of the abstraction of the device. I call it the coupling graph of the device. And so you cannot apply that directly, but that doesn't mean this is the end of the computation. What you can do is that you do a swap of a Q0 and a Q1. Now you can apply that gate to Q0 and Q3. So as you go, you have to insert a number of these swaps. It's a big optimization problem. So let's minimize the number of swaps we have, or minimize the total execution time. So if we put it in a more formal way, the layout synthesis has 2 inputs. That one is the circuit diagram. The other one is the device that you described that as the coupling graph. The output I will say, is the space-time coordinates of all the gates, and including the insert swap gates. Why it's you need both space and time? First, you want to decide at each time slot that which gate is being executed. And also you want to come up with the space coordinates. For example, here it defines Q, the logic qubit Q0 goes to physical qubit P3. Remember the mapping of storing you, the Q1 goes to P2. So that's the initial space coordinate. As you go, you may run into the problem that you want to do some computation which are not adjacent. So you have to do a swap. So this is a swap gate, can be done by 3 CNOT gates. So you get a new space coordinate, you can continue this way. So that's why I gave the term, we gave the term the layout synthesis, because if you just do layout, that's more like a placement. You determine the space coordinates. The reason we call that synthesis, it also involves scheduling, right? You figure out what gate is executed, what time step. That typically is done in the synthesis step, high-level synthesis step, in fact, in the VLSI design. So that's where the terminology comes from. That I talked about the swap gate insertion, so that's part of that. In terms of the objective, and we want to optimize the depths. That's the total execution time, or the longest execution time you have for this circuit, or the number of additional swaps you insert. By the way, this is related, but they're not exactly the same, because you can insert a number of swaps that without increasing the depth, and also the fidelity that you want the circuit to execute with a minimum amount of errors, the chances of having errors. Of course, you got to execute all the gates. Important constraint is to respect dependency. For example, you got to execute this X gate first, and then come to the T gate. And after T gate, you can execute this C0 gate. So that dependency sequence, because that all happens to Q1, have to be observed during the computation. So in this talk, my focus will be all around the layout synthesis. I will talk about the two topics. One is the optimality study, was published in the Transaction on Computers last year. And another one is the layout synthesis. And then it has architecture implications of how do you design the best quantum architectures, which I'll also talk about. By the way, as I said, we got into this area fairly recently, maybe 3-4 years ago. There's a lot of work that has been done. For example, Dmitry Maslov has done some pioneer work in this area more than 10 years ago. He's with IBM quantum team. So they process qubits layer by layer or gate by gates. If you look at all of this, they either use some heuristic approach, look ahead to see how do I minimize the number of swaps, or reduce it to some analytical solvers like satisfiability SAT solver or SMT solver. Or another class is that I think this is actually better is to use dependency, which I will emphasize, is that you don't care how the program is written, but you want to extract the absolute dependency between the computation to go that way. So you can see that easily we can have a dozen of papers in this area. I mean, also there are industry tools, and IBM operate these quantum machines in the cloud. You have a Qiskit working for a number of years. That the Cirq is from Google, and the ticket was from this company called the CQC in Cambridge, UK, right? The question is that now we have all these tools. So the first question I want to ask is that how good they are. Maybe they're good enough. There's no opportunity for my group to do any additional research. So I was curious. Now the question is, how do we know they are good enough? The problem is that this layout synthesis, you want to compute both the time and the space coordinates is MP hard. It's impossible for you to know the optimal solution. But here is where I draw some inspiration from our prior work in VLSI domain. We encounter this problem as well. The problem we have is, for example, I was working on circuit placement. The problem is that you have these logic gates, and then you want to place them in a two-dimensional surface for VLSI fabrication. You can say whether it's a good placement or not. It depends how far they are spread out. That you measure it by so-called the half parameter of the bounding box. So basically, you take the right upper corner and the lower left corner, you calculate the difference. That half parameter of this bounding box is the estimation of the wire lengths you need. You says, why don't you put them closer? I like to, but there's also millions of other gates that may have taken the space, and the connection is quite complex. So we work on this problem for a number of years. There's very good heuristics, others. There's commercial tools doing that. So back in 2003, when my project was ending, I was also curious that do we still need to work on it anymore? That maybe it's good enough. But then we ran into this problem. We do not know what is the best possible solution. After some thought, we come up with a clever idea, and we are able to construct a set of examples where I know exactly the optimal solution is. I can tell you how do I construct. It's almost like a reverse process. I do the placement first, and then I construct the circuit. It has a number of 2-pin connections. I will just draw them in adjacent connections, right? This is the shortest wire lengths you can have if you want to connect these cells. You may have some 3-pin connections, basically connecting 3 cells. And again, I will draw them in connecting 3 adjacent logic gate or logic cells. And if you have a 4-pin, then they will be all drawn in the nearest neighbor fashion. And so on and so forth. So in general, if you have an n-pin net, which means that you have a signal spans n gates, I will draw a box and square root of n times square root of n, or in the neighborhood region. So this is the smallest possible wire lengths you can get for that. So by construction, this is optimal, because you cannot reduce the wire lengths of any single net. And you can say how many 2-pin nets, 3-pin nets you want to have. I'm going to follow that exact the benchmark you have. In fact, back in those days, IBM was quite generous. They released a set of a real live benchmark suite for circuit placement. For example, 80% 2-pin net, 3% that 3-pin nets, so on and so forth. So we'll just follow that description exactly. And then we can have constructed circuits that from thousands of gates and all the way to up to 2 million objects. So for the first time that we're able to measure that our tool and other industry tools, how good they are, it turned out they are not that great. They are 60% to 150% away from an optimal solution. So we published this result. It's actually a big deal that I can see my picture in the front page of IEEE Times. And so they talk about placement tools criticized for hampering IC designs, because remember Moore's law, every generation you reduce the wire lengths by 30%. So if you are 60% or 150% away, so there's a lot of room for improvement. So we made these circuits available, and the companies like Cadence, IBM, Intel, and Magma, they were all downloading, and also including universities, to kind of test their tools. So that spurred a lot of interest in this area, and the gap actually was being reduced over 4 or 5 years, down to about 20%, from 60 to 50%. Now our own tool, we call it NPL, so it's a multi-level placer, got improved by 30% in 3 years. So this is quite significant. As I said, this is almost equivalent to 1 generation of the Moore's law scaling. So we decided to use the same idea for quantum layout synthesis. So how do we do that? It's not that difficult to do. Once you have that original idea, here you have the device graph. We want to start with that. And then we want to have a target depth. For example, I want to construct a 4-layer circuit or 3-layer circuit. How do I enforce that the circuit has to have 3 layers? And so I create a backbone with the dependency constraint. So this 3 computation all involve the qubit P1. So they have to be done in 3 different time steps, right? And just to make it more interesting, if you only have such a simple circuits, then the tools probably will figure it out right away. And then we're going to sprinkle other gates in the available time slots for computation. So this will be how your optimal scheduling will look like. And of course, if I input this to the tools, tool may recognize the pattern immediately and come out with a return basically identical solution. So we want to make it harder. We are going to scramble or permute the qubits. And then we create a circuit of this kind, which you cannot tell, obviously, that what's the optimal solution. At the end, we generate a quantum assembly program, like the program I showed you at the beginning. We give it to tools. Now you can think about, right, that in the case when we have 2 million VLSI and the placeable object, the gap was 60% to 1.5, 150%. What about the quantum computing where we only have about, let's say, 4 qubits all the way to 64 qubits? What will be the gap? At the beginning, I would think maybe similar range at the best, but there's a big surprise. And so I tell you the device we evaluated, Google, Sigmore, Riccati, the Aspen 4, IBM, the Tokyo, and also IBM, Rochester. We come up with 2 sets of circuits. One, I call the near-term feasible, has depths 5 to 55. If you remember the Google's quantum supremacy test or experiments, that circuits around 40, 50 levels. We also create a more challenging set that's from 100 to 900 levels. So for scalability study, I don't think we have the quantum device can handle circuit of that large yet with good fidelity. Gate density, we look at the 2 cases. One is we profile the Toffoli gates and we mimic that kind of a density, basically a distribution between 1 qubit gates versus 2 qubit gates. And we also look at the circuit used the quantum supremacy experiments. So we also extracted the ratio of 1 qubit gates versus 2 qubit gates. So what's the tools we evaluated? Well, I think it's more interesting to look at the commercial tools because they tend to integrate multiple heuristics, the best of art, that's the state of art out of academia. And we also look at this particular this paper from published in DEC 18 because that was the Qiskit developer challenge. So here is the bottom line. To our surprise, for example, if you look at the circuits with optimal depths, this is all near-term feasible, right? So you have these 4 devices. You have these 4 tools, and this is on the Aspen 4 device. The optimality gap is not the 60% or 150%. It's actually 500%, or 5x all the way to over 10x. So these are the different tools, published academic tools, and the Google, IBM, and CQC. So this is actually on the Google Sycamore device, very similar trend. Since this is an IBM sponsored talk, I just want to double check that IBM result is correct. This is actually the curve shown in our paper in the publication. We're using a version of Qiskit January 2020 last year. So I told my students, and when I accepted the invitation, let's run it again. So we took the version, which is a December 2020, just last month. Very much similar. So you can see that the gap is 5x to 10x away, over 10x away from optimal solution. If you scale to look at the larger circuit, remember those are level or depths 100 to 900. You look at the result on these 4 different devices. So this is a circuit depth. This is a CQC we're looking at. This is a IBM Qiskit we're looking at it. Again, the gap is somewhere from 5x all the way to over 10x. I'll come back to this diagram later on. There's some other subtle messages I want to communicate. So that gave us a good motivation. We said, wow, despite there's 20 years of research history on this topic, in fact, it's far from perfect. So we should work on it. So in fact, when we work on it, we want to get an optimal solution. So we look at the sort of the best published result 2 years ago, working on optimal layout synthesis, trying to understand what's the approach taking. For example, this is a fairly recent work from University Kepler, Kepler University, Johannes Kepler University in Austria. So they give you a formulation to compute the optimal layout synthesis. I will come back to talk about some limitations, but the attempt is to give you an optimal solution. But the complexity is very high. So they will introduce variables, basically saying if the qubit Q is placed at the physical qubit P at before the gate L, then you assign this variable to be 1, otherwise you assign it to be 0. For example, you look at the 0, right, that is that placed on physical qubit 2, so that's why you have this variable to be 1. All other variables will be 0. And if you look at this variable, that Q0 will be placed on physical qubit 3, and because there's a swap gates and before gate 4, so that's 1. All other variables of this form will be 0, and so on and so forth. But that's just part of the story. That already give you the search space to be 2 to the L2 minus times m times n. M is the number of qubits. The logical qubits, n is the number of physical qubits. L2 is the number of 2 input gates you have. 1 input gate doesn't really change the mapping, so you can ignore that. But what is more complex is that because of the swap, they have to introduce so-called permutation variables. And the definition is that this particular permutation equal to, if it's applied before gate L, that's equal to 1. Otherwise, it equal to 0. So you can see here you do have a permutation, and so then you actually and here you have another permutation. So you have a 2 permutation variable to be 1. Others will be 0. But you can have a lot of permutation variables because you have n qubits, you have n factorial permutation variables. You know that how fast this factorial function increases. So that's why this approach is very difficult to scale. And we try that with this simple adder circuits that 4 qubits, right, that we end up having over 1,500 variables and a lot more constraints to solve. And this eventually will be sent to a SAT solver to get optimal solution. So we decided to improve on this. So now our approach first is to come up with a more compact encoding of the solution space. So here's now our definition of variables. Remember, we defined the layout synthesis problem as computing the space-time coordinates of every quantum gates. So the space coordinates is XL for gate L, and the time coordinates is TL for gate L. And this GL can be a single qubit gates. In that case, XL is just a physical qubit you're mapped to. But the GL can be a 2 qubit gates, and in that case, XL will be an edge in this graph. Remember, we can only go to the edge which are connecting the adjacent qubit. You cannot map to a pair of qubits which are not connected by edge. And then we introduce this variable pi qt. Basically says if logic qubit Q is mapped to that physical qubit to this particular qubit at this time t, that's the definition. So let's look at a simple example. Again, this qubit Q0, that's mapped to a physical qubit P3 at time t, right? So that's where you get that. And it also mapped to still mapped to physical qubit Q3 at the time t1, so the pi 01 is also 3. It will remain to be 3 only after we apply the swap gates that it mapped to P2 now. So that's why logic qubit 0 at timestamp 8 goes to physical qubit P2. So keep this in mind is that you will actually, this mapping function doesn't change very often. We're going to take advantage of this later on to further simplify the formulation. At the very end, that once computation at the end is still at the time step 14 is still mapped to physical qubit that 2. So right away by this encoding, so we can have a more compact space. Now we can see that the exponential only in terms of the m and the t, because you can do a transformation. So this will be 2 to the log n of the mt. Compared to the previous approach, is actually exponential in terms of n times m times t. So later on, I'm going to further knock down another exponent that the t will go away. You will see that.
Really quick,
we have to deal
Professor,
with swap.
we do have one
Please.
quick question in the chat. Sorry to interrupt. Just a clarification question. Someone wanted to know, in the most general sense, the difference between a logical and a physical qubit.
Oh, okay. Thanks for asking that. The logical qubit is the one we write the program that you'll refer to some qubit. For example, this Q0, Q1, Q2, Q2, Q3. These are all logical qubits that involved in our program, right? For example, this gate X operates on Q0, and this gate X operates on Q1, and the gate G8 operates on Q0 and Q1. Physical qubits are what you have in a device. For example, in this IBM device, I can name them to be P0, P1, P2, P3, P4. So we have to do that mapping. One is a physical qubit is in the device. Logical qubits are referred in the program.
Okay, great. Thanks.
Yeah, thanks for asking. Remember that we also have to deal with swap, and in the previous approach, they have to introduce permutations, but that's where the n factorial number comes in. And so in our case, we have a very lightweight treatment. We just say, hey, is this swap happening at the time t? And if so, it's 1. Otherwise, it's 0. So in this case, that obviously the swap is happening at is ending actually at time step 7. So that's why, and they swap P2, P3. So I have that variable equal to 1. This is the only swap we have in this solution. All others, E's and T's, you have this delta ET that equal to 0. So what's the objective? We can actually minimize steps as an objective. That's just the maximum TL. Remember, that's the space coordinate, all the qubits. All the swaps, I add up all these swap variables. Remember, only when the swap happens, you get a 1, otherwise all 0. So it's very easy to formulate. And then we can also optimize fidelity. The fidelity typically has multiple terms. The first term is the fidelity or the measurement. Right, the second term is the fidelity of the single qubit gates. The third term is the fidelity of the 2 qubit gates, and finally the fidelity of the swap gates. And it's written in this kind of a product form. In our optimization, we'll take the log, so it's they become additions. Now I want to convince you that with these variables, that we can actually get all the constraints specified. First is the validity constraints. So for every mapping targets, that this variable got to be a node in the coupling graph, right? So basically have to go to a particular physical qubit. That's easy to specify. And the valid time coordinates, and we just have to set up a maximum time to be t. For example, you can compute the circuit, the depths, longest dependency chain. You can add some constant or with some small constant multiplier. Start as an initial guess that if later on that you don't get a solution, you can always increase this t. Under the valid space coordinate, so you have a GL as the single qubit gates. So that in that case, to go to the physical qubit. Otherwise, it goes to the a physical edge in the graph. The only kind of a constraints with an ordering constraint we enforce is the dependency constraint, right? If the gate GL depends on the GL prime, so we want to make sure that it's scheduled at a later time. TL is larger than TL prime. It's linear constraint. So that's the example. For example, gate 8 depends on gate 4 because you have here the gate 8 that depends on gate 4. So I want to make sure there's a dependency edge on that. So I want to assure you all these constraints are low order polynomials with n and t. Another thing is that you want to make sure that the mapping can allow us to compute the space-time coordinates. So for example, I map this gate logic qubit 0 at the time 0 to physical qubit P3. So if that's the case, it really says that the G3 at the T0 should be executed at P3. Is that the case? We can have this formula to enforce that. You can rewrite this. This is a first order proposition. Eventually, we're going to call SMT solver. So this is all can be handled by the solver. So again, low order that the polynomial into the number of constraints. Now we have a number of swaps that we got to model. So what are the legal swaps? First, you have to make sure the initial condition is satisfied. Basically, when we start with that, you cannot swap because swap in our formulation, you can assume it takes 3 units of time. Or you can later, that's a variable you can decide. It can be 1 unit of time if you prefer. But anyhow, so there's some initial conditions you want to satisfy. You want to make sure there's no overlap in swaps. For example, if you have this swap and you want to propose this swap, it's a problem because you already have another swap, both involve P2. So that's not an option. So you can actually have the implication of this kind. If P2, P3 involve a swap at the time step 7, then P2, P0 has to be, cannot be involving any swap, has to be 0 at the time step 7. In fact, this is not just for this pair, right? It will be for every pair involved in P2 or P3. And then you also want to make sure there's no overlap between swaps and the original gates. For example, I have this computation between P1 and the P2, involve P1 and P2. So you cannot put a swap here, involve P1 again. So the way is to do that is also, you can write it down, basically say, if I have this gate 10 involve P1, P2 at the time step 10. And this is the gate, and also the time of this one is step 8. Then I cannot have P0 and P1 at time step 8. It has to be 0. Okay, you cannot do this swap. So if you count that, you will have again a low order polynomial in terms of number of constraints. So the final rather nasty the thing you have to handle is the mapping transformation that implied by the swap. So when there's no swap, it's very easy. A qubit Q is mapped to P3, it stays on with P3. But at some point that you're going to apply a swap. You basically wants to say if there's at the time that 0 that it mapped to P3, and then there's no swap, and then it will remain to be P3. But at some point you actually have a swap. So for example, at time step 7, I map to P3, and then I have a swap at the ending at time step 7, P2, P3, that equal to 1. Now my new coordinate, that the time coordinate will be P2 because P2 and P3 got swapped. So that's how being implied. So nicely, you can see this formula can be done in first order logic very easily. Since we're looking at these possible pairs, and so we do have to introduce quadratic, but not exponential. That's the big difference. So if you summarize that all the constraints we have that the validity constraints, injective mapping, dependency, and the consistency between the space-time coordinates with the mapping variables, and the validity of the swap, and also the transformation implied by swap. all together is in this order. You add them together. Because you can say, what about the n squared term? Because n squared term typically is assumed by the L. The L is number of gates because n is smaller than the L in most cases. So in comparison, the DAC19 work I mentioned from Willie's group, that they have two input qubit gates, m number of physical logical qubits, and n factorial, that's the physical qubit. This factorial term is very, very expensive. So the key advantage, let me just to summarize. So in our case, we have n times t variables and n times TL constraints in comparison with the leading work optimal solution that you have basically you have L number of two input gates times n factorial, and the constraints also is involve n factorial term. In terms of the complexity result, is actually subtle but interesting implication. So with our formulation, you get a polynomial certificate that so you can easily argue that the quantum layout synthesis is NP. In fact, it's not clear if you use this formulation. This formulation doesn't give you a polynomial certificates because just writing down the expression that you have an exponential number of formulas to deal with. Another advantage we have is that since we use the gate dependency, so we use a minimum amount of constraints to impose the gate order. So this is actually the dependency constraints enforced by us. Why do we have, for example, edge from 8 to 11? Just because they involve the same qubits that you have to apply gate 8 first and then apply gate 11. On the other hand, if you look at again, the stack 19 work, where they actually have to have additional dependency constraints because they process gate by gate, so that introduce some artificial order. So there's more constraint. In fact, although their solver can return the exact solution, but the formulation took away some optimality as well. So that's the main engine we have. I'll come back to tell you that in fact we can further simplify what we have. So this is an important observation made by my PhD student Daniel. He's actually the co-author on both work. So he said, look, that this Q0 is mapped to P3 for a long time before it make a transition. They make a transition only when you have a swap gates. So let's figure out where we will put in swap gates first. So you will give it to the solver that you relax the constraints. You just want to first find out where do you have to swap. And then all these gates will be collapsed into a blocks. Then it turned out in our case, we only need two blocks, block 0 and block 1, and separated by a swap. So, and then the variables that in this case, you can reduce that from a number, the timestamp goes down from 14 timestamps to 2 blocks. Basically, you do some computation in the first block, you do a swap, you do another set of a computation in the second block, right? The number of blocks is far less than the number of timestamps you have because you don't have to do the swap that often. You may ask how do you compute the blocks? How do you get the block information? Oh, by the way, let me just finish. After the swap, and for each block, you can schedule it in a trivial way because you can do the, for example, as soon as possible scheduling because you don't have to do any swap and each qubit will stay on the same physical qubit for the computation. So that can be done in the post-processing step. So let me answer the question that how do you compute the block? It turned out it's very easy to compute using almost exactly the same formulation. Remember, we have all these constraints. We change the bound to the number of blocks we have. Of course, number of blocks cannot be more than the number of logic gates. So that's a safe bound. You can start from there. But a lot of time you can be more aggressive to start with. And mapping, you don't have to do anything. The only thing we really need to change is to change the dependency. Remember the dependency I used to say, if a gate depends on another gate, that they have to be scheduled at a later time. Now you change it to be, they have to be scheduled later or in the same block, because a block can do a number of computations. And no changes for these constraints. And you can relax. You don't need to enforce the overlapping conditions of original gates. And then the mapping transformed by the swap, you don't have to change that either. So with this modification, we can actually get, when we get the result back, you naturally will get the block information. And then remember, you followed by post-processing using ASAP scheduling. Basically, you schedule the gate as early as possible. So that will be the optimal solution. So now, in summary, that we reduce the number of, we reduce the complexity, again, very significantly. So this is NT, for example, in constraint, now becomes NB. N is the number of physical qubits, T is the time steps you have to go through. So you can take 40, 50 steps, right, to do a computation, but the B is the block, basically, how often do you do the transition? So that's much less. So we typically see a small number, 2, 3, 4 in that order. So you can think about B as a constant. So really that we compare, for example, in prior work, and the huge amount of complexity reduction. So compared to the one without using the transition-based formulation, we got over 400x speed up. So we made comparisons that now we have an optimal solution. For example, we compared to Qiskit that you may remember from the chart, they were actually the one give us the lowest optimality gap. So compared to them, that looking at the geometric mean, that for small circuit, and we are getting 76% reduction. That the 70s, and large circuit we get more reduction, and also the QUEKO circuit is very significant. We also compared to a more recent work that out of Princeton. It's actually to optimize fidelity. For small circuit, the gap's small, 2 to 7%, but for a large circuit, we can have a 2x advantage. Before I end, I want to talk some real life applications that before these kind of synthesized circuits or these circuits have meanings, but it's not so useful because we seldom use quantum computer to do arithmetic computation. One application area we look at, people look at, the community look at it carefully, is to use quantum computer to do optimization. So there's this class of application called QAOA. So for example, graph maximum cut is a popular application in this class, where you want to separate the graph into 2 parts, and you want to have as many edges crossing them as possible. It's an interesting problem. There's also the counterpart is to minimize the number of edge crossing, but that's another different story. You can formulate this in that introduce these variables that z variables depends whether they are in one partition or another. You can give them value that +1 or -1. You end up the objective to maximize this metric. So this one actually can be solved by a quantum device that, with high efficiency, because this ZJZK has a correspondence to 2 qubit gates like a ZZ phase gate. So that's why people are using quantum devices to solve the max cut problem. So we are actually, this is some work that we read a paper from Google. We kind of doing similar kind of experiments of the same scale. But when you come to real life problems, even interesting observations you can make. you find out that these ZZ gates can be commutable, that you can permute them as long as they do not overlap on qubits. For example, this 4 ZZ gates can be rearranged into this one. Now you can say, hey, how do I formulate it in my optimal formulation? In fact, it's quite easy. We make a distinction between dependency and a collation. So here you cannot put these 2 ZZ gates in the same timestamp because they have a collision here. On the other hand, that you have these 2 ZZ gates that can be put at the same timestamp because they don't have collision. They have a force dependency, right? So once you introduce these concepts, and again, that I think the Google paper was using a ticket for the experiments. So we compare the tickets on these examples, we get a 70% reduction on depths. So this is what ticket has in terms of the swap count. Okay, this is the depth. Maybe let's start with depth first. Close to 30, and the OLSQ, what we have with transition based, we can get it on less than 10. And after this, we relax this dependency constraints, which is still correct, that we can get it to even smaller depths. This is in the swap counts. For example, the largest, the 3 regular graph, you look at it, they are in the order close to 40. We can get it under 20, but with further relaxation, it's just a little bit over 10. Okay, so so that's the result. It's also in the paper we have. By the way, both papers that you can get it from my website online, and my PhD student Daniel Tan is a co-author, and he also have the software or benchmarks open source. So what's the next step in our research? The next step is want to do architecture evaluation. Because now we have an optimal compiler, although it's just for one step, but I think it's for an important step. So you will see this kind of architecture diagrams, either published by the industry or in the literature. Now I can ask the question, which one is the best? There's many ways to look at it, but one important angle is to see that what the compiler says, right? What result that they give it to you. So this is where we'll be very interested to work with IBM or other industry partners. And the question is, what metrics do we use? So that on the software side, for example, it can be the mapping cost, the error correction embeddability. On the hardware side, and this fabrication tolerance and the complexity of the control systems. We don't have all the information, but that's why we hope we can team up with some partners to look into this. The reason we are interested in this problem, again, is kind of motivated by our experience in the VLSI domain. I want to share you a little bit a story we have for FPGA architecture evaluation. So if you go back 20 years ago, or maybe 25 years ago, the leading FPGA company, that's Xilinx, they had a very interesting architecture called the Xilinx 4000 FPGA family. So what it has is that they have two 4-input lookup tables. A 4-input lookup table can implement any 4-input Boolean functions connected to a 3-input lookup table. So altogether, you have 9 input. So the question is that what function can it implement? So we know for sure it can implement all the 4-input functions. In fact, if you do a simple Shannon decomposition, you know this can also implement all the 5-input functions because there are 2 cofactors. But it can implement up to 9 input functions. Which set of 9 input functions can you implement? So they do not know. So this is actually, I think the quantum computing is at the stage that different companies propose different architectures. A lot of time, they may not know that the benefits or limitations of each architecture. So about the year, close to year 2000, that we come up with a complete characterization using Boolean mapping, which says, we know exactly what set of functions can be implemented. I called my friends at the Xilinx, Steve Trimberger, he's leading a lot of engineering effort. I said, so we have this characterization nobody has. He was very excited. Overnight, they sent us 1,700 examples to test. I was surprised by the efficiency, how fast they can come out with examples. So we tried them, that we can map all of them to this SC4K CLBs. So I asked him, and I said, wow, that's very impressive. How did you come up with so many examples so quickly? He said, well, these are just the customer complaints we accumulate, and our tool cannot handle them. But we're looking for solutions for that. So was the first time we have that. But with that, like, we can tell them a lot of information. For example, we take the benchmark circuits and we do the mapping. We can tell them, your architecture actually can implement 96% of 6 input functions and 88% of 7 input functions. Not only that, we can do a lot of what-if analysis. Remember, this is their architecture. We can say, if you change your 3-input lookup table by a 2-input multiplexer, what happened? And if you change that, you throw away one 4-input lookup table, what happened? And then you vary the input of one of the lookup tables, what happened? So we can do all this what-if analysis. So this is actually exactly what we hope to do that with the current quantum devices, because you're just starting, I would not say from scratch, it's in the very early days of quantum computing. I think we want to design the right architecture with the best efficiency. So we actually put together a flow, for example, people can use to evaluate FPGA architectures. We hope we have similar flow to evaluate quantum architectures. Even with the data that published so far, okay, this is just to show, for example, this is the work I had with my former students, Lei Heath. He's also a faculty member at UCLA now, to evaluate how do we design power efficient FPGAs. So you can go through the synthesis mapping, layout driven, place and route, and we come up with the power analysis and the feedback to the architecture design. So even with the result we published so far, that you can actually get some interesting insight. Remember, I showed you these slides. That I told you that there's some subtle messages I'm going to come back to point out. So here's the message. If you stare at these 2 sets of graphs that long enough, you'll realize, that the IBM Rochester architecture is the troublemaker, because you have actually worse mapping result compared to the optimal solutions, both by CQC, the ticket mapper, and also by IBM's own Qiskit mapper, right? Compared to, for example, the Tokyo architecture. That just reminds you that the architecture we evaluated. This is the Rochester architecture. This is the IBM Tokyo architecture. I'm sure you have IBM tools that the Qiskit running on these architectures every day, every hour. But you don't have this kind of insight because you never know how well they perform. So this is the first time I can tell you the optimality gap. Of course, this is an optimality gap on this specially construct the QUEKO circuits, but I think it's also meaningful. I think it kind of gives us some message saying one architecture is more difficult than the architecture. And does it worsen the difficulty? And it's worthwhile to be considered. Without further kind of the physics information, that I cannot give you a cost function to measure, but we'll be happy to work with you on that. So I think that concludes all the talks, all the topics I want to cover in this talks. And as I said, this is a joint work with my PhD student Daniel Tan, and the work is supported by the industry partners in the Center for Domain-Specific Computing. If you are interested in involved in our research program in this area, please talk to me, and so I will show you how to sign up to be an industry partner. Thank you. I'll be glad to take questions. Olivia, I hope that the timing is all right.
Oh yeah, that was great. Thank you, Professor Cong. We do have a couple of questions. We had a pretty active chat throughout. So first of all, thank you very much. I think that was really enlightening and a great talk, and obviously it has some pretty wide implications. So let me go back and figure out what that one question was I saw. Okay, so someone asked, have you tested this methodology with the native gates of different quantum technologies? For example, the CZ for spin qubits, XX for trapped ion sets, and so on.
Okay, that's a good question. We haven't, but this benchmark is available. In fact, I'm just impressed by how fast the community react. In computer science, we submitted a conference, and the result get published after 3-4 months. And apparently, in this community, people has a habit to deposit it into archive. The moment we deposit in the archive, within a week, there are people running this and tell us what kind of a result they have. So we have a fairly small group, and we are not doing all these experiments, but the benchmarks are online. I really welcome you to test it out. I'll be very interested to hear the feedback on that.
Yeah, I think that's a really good project for a lot of the people working in the community now. So that is a good point. Another question we had today is how these optimal claims change when there are mid-circuit measurements and feed forward, because this obviously has some important implications for error correcting circuits.
Sure. So if you have a mid-circuit measurement, I don't think the depth or the swap count will change, but it does change the fidelity metric. So I think that we need to sit down and then with more kind of a careful consideration whether that formula we have, that because we do have a measurement term, but that was all happened at the very end. We probably can introduce that, and if you tell us where you need to measure. So that's probably can be incorporated in the formulation.
Right, okay, makes sense to me. Let me just make sure there aren't any other last minute questions here. I think we've pretty much addressed everything that was going on in the chat. A lot of people were also asking how you know which physical qubit is being mapped to which logical qubit, and if there would be any idle qubits when you're doing this, what you would do with those necessarily.
Oh, that's a good question. Let's go back because that's an important question.
Yeah.
It all depends on the function. This is the problem when you have a lot of animation.
I thought the animations were super helpful, by the way. I thought they were like the perfect
Thank
use
you.
here.
Right. So yeah, maybe this is good enough already. So the logical qubits, so this example, it's somewhat simplistic. It turned out that we have 4 logical qubits, Q0, Q1, Q2, Q3. And here I only showed you that 4 physical qubit, but the device has 5 physical qubit. So you can actually add another line, that's fine, because sometimes that you can be mapped to P3, and after change, obviously Q0 is mapped to P2 now. And for example, you could actually have a P4, which is not showing in this diagram. We just never map to that, right? So remember now our formulation is that we have this notation. If I go back a little bit further. Yeah, maybe this is, yeah, so this is already good enough. So for each gate, we have this XL that map to a physical qubit that in the coupling graph. It goes to a subset of them. For example, you have 5 qubit gates, that you have 5 physical qubits. I may just use 4 of them, but that's fine. But there's 1 qubit left not being used, so that's not a problem. It's taken. It will not change the formulation. And then not all the edges will be used either, right? Swap will be carried out and on certain edges, but there's many edges. We don't need to have the swap gates. We don't need to have the. They can be used for CNOT and for others, but it may not be every edge will be used. Does that answer the question?
Yeah, I think it does. Sorry, I didn't realize I was on mute. Okay, I think that pretty much sums up all of the questions that we had. Oh, nope, sorry, one more just came in. I'm not sure I understand this question perfectly. How is the entanglement between the physical qubits, how does that affect the entanglement between the logical qubits? Okay, I think I understand what they're asking now. So is the entanglement
Right.
process difference between the physical qubits and the logical qubits? I think that's what they're getting at.
Yeah, if you have an entanglement that is done by 2-qubit gates, right? And so that have to be mapped to a device edge. So that where the entanglement can take place. Okay, so maybe this is the one. So remember that if you have this kind of a C0 control NOT gates, and you have to be mapped to a physical edge that in the device. So that's where the entanglements can take place. So that's
Right.
exactly the reason you cannot map to 2 qubits which are not adjacent in the physical device.
Right.
Right.
Okay.
So we'll make
me.
sure, yeah, we'll enforce that map.
Yeah. Okay, I think we have answered all the questions now. So I just want to thank you again. This was a really enlightening talk. I know I personally learned a lot, and this is not normally the type of thing I think about. So thanks again so much for being here and taking the time to talk with us today.
My pleasure. Thank you so much.
All right. And thanks to everyone for tuning in. If you like what you saw here, you can feel free to subscribe. We have these seminar talks at noon on our Qiskit channel every Friday. So with this, I just want to thank our speaker one more time, and everyone have a great rest of your day.
Thank you.